Yeah, I'm making another video, draft physics video production. So I did attempt this video once before, it didn't work out. But anyway, fractal woman. So is a person who has a theory. I fundamentally disagree with all the elemental elements, all the elemental assumptions about how the universe works. She sort of believes there's a pattern reoccurring, maybe infinitely. I don't really know that part, but like a fractal, it's a mathematical arrangement that creates the big universe, and the same mathematical arrangements creating the small universe, kind of a theory. And of course, I reject that because they have nothing in common, and we see a lot of the universe, and there's no pattern making in any dramatic way. Beyond galaxies doing gravity, there's just no evidence of any positive and negatives. There's no nucleuses. There's no formation of any of the mechanics that we know is kind of essential to the small universe, like charge. That phenomenon is not apparent in any way. And it's sort of missing the elements that you need. The element moving the speed of light versus the slow moving, material bit. It's missing the pieces. So the big universe is just a reflection of what the small universe does, and the small universe is doing something quite different than the big universe. So anyway, fundamental disagreement. I think she's an etherist, pretty much, and big on waves and all of that crap. Also, all stuff that I reject. But anyway, she's a reasonable person. I don't think she's in any way desires to be inaccurate. I think she does care about getting it right. And so I figured I'll do a response video because she's talking about ferrocells, and she has pointed out some of the facts about a ferrocell, and I don't know why those facts don't seem to have had much of an impression on her, in terms of the fact that she still seems to think there is something in the mechanism that is bending light in some specific way relevant to anything more complicated than a bent mirror bends light. I mean, you can have a mirror that's straight and you see an accurate image, and you bend the mirror and you'll see an inaccurate image. It seems clear the ferrocell is a bent mirror. It's merely showing you something common, like iron filings lining up, and it's showing you a skewed view of it that gives you a misimpression. You're only seeing certain ones, and the certain ones are creating a warped pattern. So yes, the warp is dependent on where the iron filings are, but they're not representing how the iron filings are lined up. So again, I would argue anybody who believes in the ferrocell, go look up ferrocell and microscopic and see what the little bits are actually doing. And you'll see that they're doing what a little magnet would do, a little piece of iron, and they're lining up. So I guess let's first do that just for quickly. That these patterns that we see around magnets, that we understand a magnet based on what it does to something. The point of physics is really to get to the core of it. Why is it doing it? Okay, so there's two images of magnets. Let's see if two colors works. I don't know if it will. Ooh, that doesn't even work. Let's try turning the light on, see what that does. All right. Solar light. Oh, it's much worse. Great. Glad I turned the light on. Alright, anyway. Just have to endeavor to persevere, folks. Okay, you really can't see those difference in colors much, but who cares? So the point is if you do iron filings on a piece of paper, right, so you're not allowing the iron filings to do what they want to do. You're suspending them. You're stopping them in their motion. And then you can create a pattern, okay? But it's not a pattern that's natural. The magnet won't do that naturally. The little pieces won't line up in these locations. They'll fly into the magnet. They'll become little magnets, and they'll do exactly what little magnets will do, and they'll fly right into the magnet. So this is an unnatural condition. And so these lines aren't real in any sense. They're something manufactured. Okay, they're not something naturally occurring. There's something occurring because of a circumstance. You're preventing magnets from moving further in, and the magnets are lining up. They're being created. Okay, the iron is being magnetized, and they're all magnetized in the same orientation. So it means lines repel each other. So obviously there's space in between, and you know, those are the rules. So anyway, you get this picture of a magnet, and that's one image. Now you can get, if you look at just a bar magnet in some other circumstance, you know, where you let the filings move to the magnet, you'll see the pattern will just be this. Okay, there'll be a bunch of stuff on both ends of the magnet. Okay, more stuff piles up on the ends and piles up on the sides, and that's the image you'll get. Okay, again, it's just another image. I'd say this image looks more like reality, but that's the image you get. So it's a different image. It just depends on what you're using and how you're using it to measure the field, to see what the field does to stuff, and what it does to stuff that you create limits on what it can do. And it's really important to understand that you've limited what it can do. So anyway, that's a place to start. Just understanding that lines, because somebody can draw a line representing something, doesn't mean they're representing something real. So this little pattern she has on her drawing here is a pattern basically illustrating the inverse square law. The further away the little lines are, the colors don't mean anything, so don't be fooled by them. The further away the lines are, it means the weaker the force. The closer they are, the stronger the force. And the force is just implied to be in a direction, in or out, doesn't really matter. And so you're just measuring how strong the force is at a location, and it's equal. The same force at that circle, the same force at this circle, it would all have the same amount of intensity. But it doesn't really show you what the force is, or where the force came from, or why the force exists. It's just, again, a representation of what something will feel at those locations. If I put a charge there, what will it do? And how intensely will it do it? But it doesn't, it's not showing you the force. It's showing you what they call a field. That is, how the force, what its effect is at the different locations. And it's just showing you that there's symmetry, that the force is even. Okay, and then unless I start to disturb it with another object. Alright, so the first thing that has to be understood is, okay, so when you have one of these ferrocells, you put a magnet in it, and you have the magnet face up or face down, whatever, you know, north side up. The little filings are going to line up just like they would in a regular magnet. Okay, they're just going to be lined up in lines. They're going to all be little magnets, and they're all going to line up pointing, okay, towards the magnet in the right south, north, south, north, south, north, south, north. And they're all going to keep doing that. And again, they're repulsive, so they're all going to repel each other. So they're going to essentially create these lines. And that's what's under the glass. So under the glass is just these spirals. That's a fact, okay? It's a fact proven by looking at them with a microscope. That's what they're going to do. And so you have to account for, this is what you see when you look at the thing. So you shine a light, so now you can look at it. And what you're going to see is something going like, I can't remember exactly how the curve goes. I think it goes like this. Alright, so that's what you're going to see. That. Alright, now so even though everything is lined up straight, okay, there's not a crooked line in under the piece of glass. Under the piece of glass, there's not a single thing doing anything crooked. It's just dead straight lines radiating from the center, and that's it. But this is what you're going to see with one LED. And if I put a bunch of LEDs, you can sort of understand that line just moves to here, and it moves to here, and it moves to here. So that's what you're seeing. And the reason why you're seeing that is because of these lines are all made of little bits of stuff, and that there's distance between the little bits, and they're refracting the light, so they're spreading it at angles, and you're only going to see the light as it's reflected back to you. So this LED is shooting the light, and most of it's not going to reflect, but it's going to hit certain things and then reflect at just the right angle to hit you, and then another piece will reflect just the right angle to hit you, and then another piece over here, it's just the right angle to hit you. So it's just this angle you're looking for. What creates the right angle? And what creates the right angle is a different spoke for each part of this curve. So this curved line is really made out of pieces, okay, little hunks of curve. all right? And the little hunks are on different rails of the iron filings. So you're not seeing anything that actually exists under the glass. You're seeing just a composite of where the angles are correct to get it back to your eye, to get this light to come back to your eye. And that's all it is. So mechanically, it doesn't show you anything about real dynamics. It's completely obnoxious almost to the truth. It's showing you a line that has nothing to do with the actual function of the magnet and the iron filings. There's no truth value in it. There's no value in it as information telling you how the thing works. All right, so continuing to the more important charge elements of this. So they're using these, what they call isopotential lines. And they're just lines, again, the closer they are together, the stronger the force, the further apart they are, the weaker the force. And the thing to understand is these are north-south, so the flow is opposite, in the sense that one side is pushing, okay, and the other side is essentially pulling, which is exactly the same direction, okay? I mean, it's the same direction. So even though they've sort of made it look like those are two opposing forces, they're complementary forces. And the only argument being made is that, of course, these lines around this thing would be small here, small, small, then get wider, 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 wider. As you get further away, it gets weaker and weaker. Well, obviously this force, when you take a weaker force here, they're both adding. The force is both in the same direction. So even though this is a weak force from this one, it's added to the stronger force of this one. So obviously it pushes more, and these lines have to be closer together. That's just what's going to happen, because you're adding in the same direction. And so you can't even see the lines. They're so compressed in there, in the middle. They're just like, looks dark and red, but it's not. There's more lines here, okay, because there's more force, because you're adding two forces. That's all that is. And again, the little bends in the lines of the LEDs, those are all different colored LEDs, and each one is making a line, blah, 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 blah. And so you're just seeing pieces of different sections. You're seeing a piece of this one, and then you're seeing a piece of this one. You're seeing a piece of what would have been this, and you're only seeing a piece of it. You're seeing this piece, and then you're seeing this piece, and then you're seeing this piece. You're just seeing the pieces in different places. So anyway, so it's all can be dissected and understood that this isn't showing, that's not going to show you reality. All right, so let's get back to Maxwell and Faraday and the Heaviside and Steinmetz and all of those people who all relied on some idea of a line of force and a field line. And let's understand the simple mistakes made in recognizing the two different things. So she gets this basic argument in the sense that she understands that this is a real drawing. Now this one's representing the force in a sense with the dotted lines. That's how the force actually moves, and that these circular lines are just representations of where's the force the same. Obviously the same distance from the center, same amount of force. So there's just two ways of understanding the same thing. Now in Maxwell's math, which is Gaussian and Ampere's math, it was understood that you're not drawing every line of force. You're just drawing a representation of the force. And so you can, this is an arbitrary number of lines you can draw, and that they just represent, okay, this separation between the lines represents the rate at which they degrade, which would be the R squared rule, generally speaking. Why am I putting squares down there? So generally speaking, that's what you're illustrating. And so if you just used 3 lines, you could do it. If you used 100 lines, you could do it, and it'll just be more exact the more lines you use. But you can obviously mathematically understand that if I use 10, I could always subdivide the 1/10 into 10 sections, and I could always subdivide those into tenths. So mathematically just makes it easier to understand. But the basic idea is that the force has the lines of force have a direction, okay, and they're just coming from the object. But the direction, again, is we understand from the mechanics, is kind of arbitrary in the sense that if I have a negative charge that I test it with, then it's a force going that way. If I test it with a positive force, then the lines are going in. So that's just the only tricky part about it. So you know there's a trick to it. All right, you know that somehow both objects, the positive charge and the negative charge, are doing the same thing. They're making a straight line force, but somehow the force looks entirely different depending on whether it's a plus or a minus. It's shooting things at me, or it's somehow pulling me. Okay, and then you get into this whole push-pull impossibility argument. Obviously, I would argue it's not pushing anything, it's just eliminating a pressure, and there's more pressure on the outside and it pushes. But anyway, it doesn't matter. So they, Maxwell is often taught, and even Susskind teaches gravity by just saying, imagine it as a fluid. So just imagine that the plus charge is a drain, and a source of fluid, and that the minus charge is a drain. And so you can just kind of understand the two concepts. But understand, if I use a plus charge, it changes which one's a drain and which one's a source. So that's the part that makes this a little tricky. And it's tricky, but I mean, it's not something you can't overcome. So the idea of this lines of force, so this is what the force is really doing. Okay, so you can understand that at some point, in some place, if these are both positive charges, that means they'll do the same thing. They'll either pull something in this direction, or they'll end up pushing something in that direction. So if I use a negative charge, it'll get pulled. If I use a positive charge, it'll get pushed up. And so you can sort of just add up the vectors and figure out that's going to be the consequence. So that's not too complicated. But you could draw a line that said, where does something get pushed that strength? And you could find all the places, okay, where something gets pushed that much, that direction, and they'd probably all be, I don't know if they'd all be on that line. But that doesn't really matter. The point is, you can make some line for some arbitrary statement about how much energy something's going to, if I put something in that location, what path is it going to travel? How is it going to, which way is it going to fly? Obviously, it's getting pushed a lot by this one and not as much by this one, so the angle will be something in that direction, primarily straight, and then a little bit of added energy from that one pushing it this way. And you can figure out which way it's going to go. And then if you make these pluses and minuses, then you can have all kinds of things where it's being pushed away by one thing and pushed into another thing, and get all kinds of curved lines. But those curved lines aren't showing you the force. I'll erase one more time. So I just want to get to the fact that you don't need to add any of those lines. Those lines aren't really telling you anything. So by saying I'm gonna measure, it's like, let's understand it. Let's say if there was water, but it was water in the sense that the water didn't mix with each other. It was like an ink that didn't mix. So you were going to make a dye that was going to move through the water, but the dyes didn't actually turn color, okay, when they mixed. And it wasn't until you showed up and put a boat in there that you know which way it is. So the idea is to understand the forces are producing straight line force. Those are the lines of force. Each object produces them by an inverse square law, that is, equidistant from the source will always be the same amount of force in that direction. That's what the force is doing. And it isn't until you put an object in the field that the object combines the two and adds them up. And then the object says, okay, this plus this equals this. Or if this is pulling and this one's pushing, that if I leave here, what's going to happen to me? I'm going to leave in this direction strongly. I'm going to go this way, just like an earth. I'm going to have a motion this way, and then this thing's going to be pulling on me, so it's going to keep adding a vector in that direction, and adding a vector in that direction, so it's going to curve me into it. And I could draw that line, but that line isn't telling me anything about the force. It's just, I mean, it doesn't tell me anything about the elements that created the consequence of that being where the boat goes. So if I create a source in a boat, you don't have this idea that the boat is following some current in the water already. No, it's just obeying the fact that there's a drain over here and there's a pusher over here, and it does the addition. It figures out where it's going. So lines aren't representing anything real. They're representing what happens to a thing you put in the field. So if you put a charge in the field, what will it do? And that's all it's doing. So here was, it's not the right color. There it is. So she puts what the magnets are doing on top of, with iron filings, how they line up on top of these lines. And that's perfectly legitimate in the sense that, yes, the mixture of the force is what's going to bend these lines, in the sense that you can draw them by recognizing the fact that a negative charge here, okay, is going to move to the South Pole, and it's going to take one of this path, because it's going to be repelled from this, push this way, and then move that way. So you could create these lines, and you could also understand that these lines are getting closer together, meaning the force will be even stronger, because you're moving away from the north and you're moving towards the south, so the two are adding up, which means it's giving you more acceleration. But nothing in the force doesn't move any of these paths. None of these paths have anything to do with any force moving in those directions. The force is still going in straight lines, and it's just that they're obviously in a dipole opposite forces. It's essentially an electron and a proton, and they would do exactly the same thing to another electron or another proton put in the field. Was going to behave the same way as that. So here's all the images composited. So this drawing doesn't show the field, the force. The lines of force aren't in here. So there's two different patterns of lines, but neither set of lines shows anything but what a charged particle will do if put in the field. It's not showing you what the lines of force are actually doing. And this one's essentially the same drawing, same drawing, same drawing. So pointing out how you can draw, you can illustrate where boats go. Yes, they all agree. And I would say they all agree on what the force lines are, but understanding the force lines, it means you can finish with this idea that there's no such thing as a magnetic monopole and all that nonsense. Because obviously when atoms are polarized, they also become magnetic. All right, they're not just carrying electricity, they're causing magnetism. They're causing magnetism because you've polarized them. You've created a north and a south pole, and you're aligning them in the same direction, and that's going to make a magnet. So if you take a bunch of magnets that are going in all kinds of different directions, well, first you take atoms that don't have polarity. They don't have any length, they're just dots. Okay, so then you turn them into lines first, and then you turn all of them into lines facing the same direction. You're going to create a magnet. So do I really have to go any further to really point this out? I mean, I just don't know how to say it, that you can draw lines representing energy levels, but you're kind of cheating, because the only place you get those lines from is putting something in the field to interact with the force. The force doesn't interact with the force. The force doesn't do the math ahead of time. So the red light, as I'm pointing out, produces red light. The purple light produces blue light. And you can know that from certain locations the light's going to look purple, and it can look bluer or it can look redder depending on which part you're looking at. But you know that the light sources themselves, I guess it's the simplest way to say it, the light sources themselves are either blue or red, and they radiate the light as if, perfectly like that. Okay, and you're only going to get purple when you're in a location where you can see the same amount of red as you see blue, or If you're over here, then you're going to see more blue than red. So this is going to be a blue purple. And if over here, you're going to see a red purple. And that's all. It's that simple, but the force didn't change. The force isn't different here from the red, and it isn't different from the blue. It's just that once I put you here to look at it, you'll see how much blue there is, and you'll see how much red there is, and you'll create a purple out of that. Yeah, that's probably enough. Yeah. It's hard to know what starting point and what end point you have to get to, but so let's just summarize. So the lines of force are clearly radial. There's only one force that's causing movement, I would argue. Kind of obvious. There's no electric force and magnetic force. There's just one force. You either move it or you don't. You either affect it or you don't. You're either being pushed or you're being pulled. Calling it electricity or calling it magnetism is superfluous to the fact of what the force is. The virtual photon doesn't change for electricity and then change for magnetism. It's the same thing, the same carrier. So the whole conversation is kind of moot. And clearly electrons and protons can be imagined to behave just like a magnet. If I put them next to each other, you know, head tails and tails head, they'll do exactly what magnets do. They'll attract and repel. So it's clearly monopoles of magnetism. It's not really, in my opinion, rationally debatable. They have every feature that a magnetic monopole would be. If you could describe what a magnetic monopole would look like, electron and proton fit the description perfectly. So why is there any argument? Because you've already assigned them to be electric dipoles? Well, there are no electric dipoles, you could argue. So what's the point of talking about it? Yes, I mean free. Yeah, it's the same thing. It's the same thing. Electricity is different. Magnetism is clearly, I would argue, just a reflection from the external pressure. It's just reflecting or not reflecting. So where the energy comes from is easily solved. And electricity is a phenomenon where pressure is exchanged between atoms. That's electricity. So it's silly to talk about electricity as if it's a force being emitted. It's not a force being emitted. It's a process of conduction of pressure, transfer of it from one thing to another thing to another thing to another thing. And what is the force between those things is obviously magnetism. So the force that allows atoms to transfer their pressure is magnetism. All right, anyway, that's probably enough. I mean, she gets this, so I don't know why there's an argument. I mean, this is the basic idea. This is the lines of force. Okay, and the positive and negative is arbitrary, because if I put a positive charge in, the arrow's going out. If I put a negative charge in, the arrow's going in. I mean, so that's the part that has to be understood. But there are no arrows going in. There's just arrows going out, and the fact is you either see it or you don't see it. Electrons reflect the pressure from electrons. Protons reflect the pressure from protons. And inversely, they transmit the opposite. So when a proton's near an electron, they're both transmitting rather than reflecting. And therefore, they create no pressure between them, and therefore, they move into each other. Okay. But anyway, I mean, I'm not trying to prove my theory, tell you my theory's right. I'm just explaining where you're making a fundamental mistake in confusing lines of force with field lines, and the different ways you can draw field lines. They're not the same thing. What the force is doing is not the same as what it does to boats. The path the boat takes doesn't have a whole lot to do with what the individual elements are that are creating the current the boat's going to flow in. They keep doing their thing. The mixing is irrelevant in the pure sense. The mixing isn't something the force is doing. It's something the thing looking at it's doing. There's no purple light. There's red light, there's blue light. I can see purple, but the purple doesn't exist. the red and blue light aren't mixing with each other and making purple. I guess that's the simplest way to put it. Alright, so till the next time and such. Not as good as I wanted it to be. Whatever. I have to settle for... I have to settle. Yeah, I'm settling. That's what I'm doing. Till next time. I mean, see how it seems so obvious to me. And I guess I'm just saying, obviously people are darn understanding it. And I'm just saying, how can they not understand it? The red and the purple don't mix. I mean, the red and the blue. Oh, see, I fucked it up already. The red and the blue light are not mixing. But if you have the right kind of eye, you can make the new color. Okay, that's probably enough. So, till the next time.